Hello, this video includes information on Gibbs free energy.
We're going to talk about what's called Gibbs free energy. Okay, when we talk about the spontaneity of a reaction, sometimes it's hard for us to figure it out just by looking at the entropies, because we have to determine the entropy change for the system, we have to figure out the entropy change for the surroundings, and we have to consider what the entropy change for the universe would be. So what Gibbs did back in the late 1800s is he came up with a way to calculate the spontaneity of a reaction in a little bit of an easier way. He calculated the free energy that's available to the system when we look at a particular reaction. So this G value is what we call our Gibbs free energy. H is our enthalpy value, and T is temperature, and S is entropy. Now, if we want to calculate the change in free energy, we would just have to take the change in the Gibbs free energy value equals the change in enthalpy minus T delta S, or temperature times the change in our entropy. So this is a pretty big equation in thermodynamics. So where does it come from? Although you're never going to be asked to derive it, I do want to kind of show you that it is related to other equations. So if we were to look at our entropy for the universe equation, we know that the entropy of the universe equals the entropy for the system plus the entropy of the surroundings. Well, the entropy of the surroundings is equal to negative delta H of the system divided by our temperature. So we can just do a substitution here. Now, what we can do next is just multiply everything by T, or negative T. So this becomes negative T delta S of the universe equals negative T delta S of the system plus delta H of the system. And then if we define negative T delta S for the universe as our Gibbs free energy change, we get what we call our Gibbs free energy equation. Okay, you're never going to be asked to derive it, but I kind of wanted to show you where it comes from. What's the importance of delta G? Okay, well, if we know delta H and we know delta S, we can calculate delta G. And if delta G is a negative value, we're looking at a spontaneous process. If delta G is a positive value, we're looking at a non-spontaneous process. And if delta G equals 0, we're at equilibrium. When we look at this Gibbs free energy equation, there's actually 4 different kind of scenarios that we can have based on what the sign on delta H is and what the sign on delta S is and how that affects the sign on delta H. The first 2 are pretty straightforward. Okay, let's say that we're given this reaction here, and we're told that delta H is negative 163 kilojoules. All right, so delta H is negative, gives us the number. Well, we're going from 1 mole of gas to 3 moles of gas. So our entropy for our system is increasing. So delta S is positive. So look at this for a second. If delta H is negative and delta S is positive, now temperature has to be positive because it's Kelvin, it's on the absolute temperature scale. Taking a negative value and subtracting a positive value can only give you a negative value. Delta G can only be negative if we're looking at an exothermic process that increases the entropy for the system. Delta H being negative, exothermic is enthalpy favored. a positive delta S is entropy favored, the reaction will always be spontaneous. Now let's look at the second example. Okay, we've got oxygen going to ozone. It tells us the delta H value is positive, so it's an endothermic process. That's not enthalpy favored. And if we look, we're going from 3 moles of gas to 2 moles of gas. So our entropy is negative, our entropy is going down. So if we were to look at Gibbs free energy, if this value is positive and delta S, this value is negative, subtracting a negative is the same thing as adding a positive. So a positive delta H subtracting a negative delta S will always give us a positive delta G. So this process will never be spontaneous. It's always non-spontaneous. So it's not enthalpy favored and it's not entropy favored. It's not spontaneous. Well, let's look at the other 2 scenarios because they're a little bit tricky. Let's say that we're told we're taking liquid water and we're freezing it to solid water, and the delta H is negative. It's an exothermic process. So that means that it's enthalpy favored. It's exothermic. That's good. But the entropy is decreasing. That's not favored. If we look at Gibbs free energy, if our delta H is negative, and we're subtracting a negative, well, it's going to depend on the temperature, how big this value is. If we're at a low temperature, this value here will be smaller than this value here, and delta G will be negative and the process will be spontaneous. But if the temperature is high, this value here will be bigger. This T delta S value will be bigger than our delta H value. And subtracting a negative is the same as adding a positive. If the positive side is bigger, if it's entropy favored, delta G will be positive and the reaction will be non-spontaneous at high temperatures. So let's look at the opposite example. We've got liquid solid and we want to change it to gaseous solid. So now we're boiling water. Well, to boil water, we have to add energy in. So it's an endothermic process. That's not enthalpy favored. But we're going from a liquid to a gas, so we're increasing the entropy that is entropy favored. So if we're at a lower temperature, the enthalpy value will be favored over the entropy value. Our delta G will be positive and the reaction will not be spontaneous. But if we're at a higher temperature, the entropy will be more a higher value than the enthalpy will be. The Gibbs free energy value will be a negative value. So the reaction is spontaneous at higher temperatures. So if enthalpy is favored, but entropy is not favored, it's temperature dependent. And the opposite, if enthalpy is not favored and entropy is, it's temperature dependent. If our entropy increases and our enthalpy increases, it will always be spontaneous. If the enthalpy is negative or is positive, it's endothermic, is not favored, and our entropy is negative, it's not favored, it will never be spontaneous. But if the entropy is favored and the enthalpy is not favored, The only time it will be spontaneous is at higher temperatures. And if the entropy is not favored, but the enthalpy is favored, the process will be spontaneous at lower temperatures. That's kind of what this graph tells us here. If we have an exothermic process that increases entropy, it will always be spontaneous. If we have an exothermic process, but we're decreasing the entropy, it will be favored at lower temperatures, but not favored at higher temperatures. If we have an endothermic process that decreases the entropy, it will never be spontaneous. But if we have an endothermic process that increases the entropy, it will be spontaneous at high temperatures and not at lower temperatures. Let's do some math. Okay, that was kind of conceptual. What is the normal boiling point of liquid bromine? At what temperature is the following process spontaneous? Okay, so liquid bromine going to gaseous bromine. Now we need to know some information about bromine. So this process is endothermic. We're going from a liquid to a gas. We know we have to add energy in order to break those intermolecular forces. So having a positive delta H makes sense. We're going from a liquid to a gas. We're increasing the entropy. So having a delta S value that's positive, this value makes sense. Now, a positive entropy favors spontaneity, but a positive enthalpy does not. So let's look at our Gibbs free energy equation, and we want to calculate the temperature. So we'll just do a little bit of algebra here. We're going to first define boiling point. Okay, boiling point is the point at which the liquid phase and the gaseous phase are at equilibrium. So delta G is going to equal 0. So we'll substitute in 0 for delta G. We're going to add T delta S to both sides. And then we're going to divide both sides by delta S. And that'll give us T. That's what we're trying to find. What temperature? So we have our equation that we figured out from this information. Now we're going to substitute in our information. So delta H, we're going to substitute in. Now I changed the units. Since this is joules per mole Kelvin, and this is kilojoules per mole, I just changed this to joules, so the units are the same. So I multiplied it by 1,000. So 3.10 times 10 to the 4th joules per mole. Okay, again, I just took kilojoules per mole and converted it to joules per mole. So there's our enthalpy value. We're going to divide it by our entropy value. Notice that now the joules cancel out. The moles cancel out. We're left with 1 over Kelvin, which gives us Kelvin. So T equals 333 Kelvin. So that means that this process will be spontaneous whenever the temperature is above 333 Kelvin. If we're below 333 Kelvin, then delta G would be a positive value and the reaction would not be spontaneous. So liquid bromine will spontaneously boil at a temperature above 333 Kelvin. So let's look at another scenario. Okay, we've got carbon tetrachloride. We're breaking it down into carbon and chlorine. It tells us that the enthalpy change for this reaction is positive 95.7 kilojoules. That makes sense. Positive means we have to add energy in. It's endothermic, and we're breaking bonds in the reaction. And breaking bonds is an endothermic process. And our delta S value is positive 142.2 joules per Kelvin. And that makes sense as well, because we're going from 1 mole of gas to 2 moles of gas. So we're increasing the disorder in the system. We want to calculate delta G. And then once we do that, we want to determine whether the process is spontaneous or not. We write down our givens. We know delta H, okay, it's endothermic. We know delta S, it's increasing the entropy. We know the temperature in Kelvin is 298. And then we're going to use our Gibbs free energy equation to calculate delta G. Now go ahead and do that, but look at your units and be super careful with your units. Okay, this is kilojoules. This is only joules. So multiply this number by 1,000 so that your units are consistent. See if you can calculate delta G and then figure out what that delta G value actually means. Okay, I left it in joules. If you convert it to kilojoules, that's great. Okay, so we're going to multiply this number by 1,000. So that gives us 95.7 times 10 to the third joules. We're going to subtract from that our temperature times our entropy value. The Kelvin cancels out. We've got joules. The joules are our answer. Again, if you change it to kilojoules, you would get 53.3. I agree with that. Okay, now the important part there is the positive. Okay, in the chat, if it's a positive delta G, is it endothermic or exothermic? Positive delta G. Because conceptually, we just have to know what the signs mean. Process at this temperature is not a spontaneous process. We would need to increase the temperature in order to get this reaction to actually occur. All right, so let's add on just a little bit to this. Okay, we're going to look at calculating the entropy or enthalpy, calculating the entropy, and calculating the Gibbs free energy. So we've got our reaction here, and now we have a table. Okay, the enthalpy values are things from Chem 1. The entropy values are things that we just went over. So let's look at the delta H first. So if we want to calculate the delta H for the reaction, if we want to find out whether this reaction is endothermic or exothermic, actually, if you look, it's pretty much the same reaction or equation that we had for entropy. It's the sum of the products minus the sum of the reactants. And we're multiplying them by the coefficients in the balanced equation. So here are your enthalpy of formation values. Here are your coefficients in the balanced equation. See if you can calculate delta H for the reaction. Don't go any further than that. Calculate delta H for the reaction. Look at the sign on delta H and try and figure out what that means with respect to the reaction. Okay, so I'm getting 2 times negative 396. That's the sum of my products. Minus 2 times negative 297. Plus 1 times 0. The enthalpy of formation for oxygen is 0 because that's the free element. And you got to kind of be careful with the signs when you plug that in the calculator. And you're going to get an enthalpy change for the reaction of negative 198 kilojoules. The negative means this reaction is exothermic. It's giving off energy to the surroundings as it occurs. And that's enthalpy favored. That's good. So now let's calculate the entropy change for the reaction. Again, the equation looks just about the same. We're going to take the sum of the products minus the sum of the reactants. We're going to use the entropy values this time in our table. And we're going to be multiplying these values by the coefficients in the balanced equation, because the numbers on the table are per 1 mole, and sulfur dioxide has 2 moles, sulfur trioxide has 2 moles. So plug your numbers in, see what you get for the entropy change for the reaction. Look at the sign and see if that makes sense. Okay, so we're taking 2 times the sulfur trioxide. That's the sum of our products. We're going to subtract 2 times the sulfur dioxide plus 1 times the oxygen. And we're going to get a negative 187 for our delta S of a reaction, our entropy change for the reaction. Now let's look at that. A negative sign means our entropy is going down as the reaction proceeds. Well, we're starting with 3 moles of gas. We're ending up with 2 moles of gas. So that makes sense. That negative sign makes sense. The entropy is going down as the reaction proceeds. Now, the last thing we want to do is we want to calculate delta G. Well, we're going to take the value that we got for our enthalpy, that negative 198 kilojoules, and we're going to want to take the value that we got for our entropy, that negative 187 joules per Kelvin, and plug them into our equation. Now, the units don't match up. This is kilojoules. This is joules. It doesn't really matter which one we change. Okay, I would change the kilojoules to joules. It doesn't matter though. Okay, change them so they're the same. The temperature is in Celsius, so you need to change it to Kelvin. Plug the values into your Gibbs free energy equation. Calculate your value for delta G, and then look at the sign and determine what that sign means for the reaction. Actually, this time I kept it kilojoules. I changed this to kilojoules. So I'm going to take my delta G, my delta S, going to multiply it by my temperature in Kelvin. So my Kelvin cancels out. Now I've got kilojoules minus kilojoules. That works out well. You just get a bigger number if you converted them to joules. And we get negative 142 kilojoules. So what does that negative sign tell us about the reaction? It tells us that the reaction is spontaneous at these conditions. So the enthalpy is favored, it's exothermic. The entropy is not favored because we're decreasing the disorder in the system, but the overall energy is going down, which means that the process is going to be a spontaneous process. Let's look some more at this Gibbs free energy value, this delta G value. And it's what we use to decide whether or not a reaction is spontaneous or not. If delta G is a negative value, then we're looking at a spontaneous process. And if delta G is a positive value, then we're looking at a non-spontaneous process. And there are 2 ways that we can calculate that value. Okay, like we did in our warm-up, we could use our Gibbs free energy equation. So delta G equals delta H minus T delta S, where delta H is the enthalpy value, whether it's endothermic or exothermic, and delta S is the entropy value, whether we're increasing or decreasing the disorder for the system. But the other way that we can calculate delta G, and it kind of depends on what we're given in the question as to whether we would use the first equation or this equation. We can also calculate the delta G value and decide whether or not a reaction is spontaneous or non-spontaneous by taking the sum of the delta G values for the products and subtracting the sum of the delta G values for the reactants. Just depends on what we're given in the question. It's two ways of calculating the same thing. And when we talk about this delta G value, it's not a value that can actually be measured in a lab. So we would always be calculating how much that free energy changes during a reaction. Not necessarily how much we have at the beginning and how much we have at the end, but how much it changes from beginning to end. Let's look at a question that uses that equation. So we want to calculate the free energy associated with this reaction. And again, we've got two different equations we could do that with. We have to look at what we're given to decide which equation works. So in this case, we're given the delta G of formation for our carbon monoxide and our CH3OH. This is actually 0. Okay, free elements have a delta H of formation value of 0, so it just wouldn't be given to us. So we're going to use the sum of the products minus the sum of the reactants to calculate the free energy for the reaction. And then we can decide whether or not this reaction is a spontaneous reaction or a non-spontaneous reaction. So use the information that's given there. Really work on, how you're solving the problem when we do them, so that when you go to do your homework and when you go to take your test, you've practiced how to solve these problems in a way that's logical, a way that you can follow, and a way that I can follow. Okay, so sum of the products minus the sum of the reactants. Okay, so 1 times negative 166.3 minus 1 times negative 137.2. The 0 is in there as well. You don't have to put that in your number. Negative 29.1 kilojoules. Now, delta G deals with spontaneity. So if our delta G value is negative, good, it means the reaction is spontaneous. Okay. Delta H tells us whether the reaction is endothermic or exothermic. Delta S tells us whether we're increasing or decreasing the disorder in the system. And delta G tells us whether the reaction is spontaneous or non-spontaneous. And I agree that the system is becoming less disordered because we're going from gases to a liquid. That's not what delta G tells us, though. Delta G is going to tell us the spontaneity. So this reaction is going to take place without outside forces acting on it to take place. When we talk about free energy, it's a state function. Again, what does that mean? Well, it means we don't need to know the path that the reaction goes through. We just need to know the initial, where do we start and where do we end? So let's say we talk about we want to find the free energy change for diamond changing to graphite. Okay, and this is the information that we're given. This isn't something that we can use the Gibbs free energy equation on. We don't have delta H and delta S, so that's not going to work. And we're not given the free energy values for the products and the reactants, so we can't use that. So what we're going to do is kind of apply the fact that free energy is a state function. It's a lot like Hess's law, if you remember that from Chem 1. So let's see what we would do. We want to look at the two equations that we're given and manipulate them so that when we add them together, they give us the reaction we're looking for. So we want diamond to end up on the reactant side. So we're going to leave that first reaction the way that it is, but we're going to want graphite on the product side. That means we're going to need to flip this reaction around, which means we're going to be changing the sign on delta G. The reaction is spontaneous in this direction. That's why it's a negative delta G. It would be non-spontaneous in the reverse direction. So we leave the first reaction the way it is, and we keep the sign. We flip the second reaction around, and we flip the sign. Now, the carbon dioxides cancel out. That's good. They weren't in our overall reaction. The oxygens cancel out. That's good. They weren't in our overall reaction. And we're left with the reaction the reaction that we were asked for. Diamond yields graphite. So we just have to add up our delta G values for the manipulated equations, and that's going to give us the delta G for the reaction. And because it's negative, this reaction is a spontaneous process. Although, again, spontaneous doesn't mean instantaneous. Okay, this takes billions of years to take place, but it would take place on its own without being forced to take place. So let's look at another one. Let's say that we're given these three reactions, and we're given the free energy values associated with these reactions. And we want to calculate the delta G for the formation of phosphoric acid. Now, phosphoric acid is H3PO4. And when we talk about the formation of a compound, it's being formed from its elements. So it's going to be formed from phosphorus, hydrogen, and oxygen. So that means we want phosphorus on the reactant side. It's in the first reaction and it's on the reactant side. So that first reaction is going to stay the way it is. We want hydrogen on the reactant side. It's in the second reaction and it's on the reactant side where we want it to be. And we want oxygen on the reactant side, and it's in the second reaction on the reactant side. So we're actually not going to flip any of these reactions. So what's going to cancel out? Well, the P4O10, the tetraphosphorus decoxide, would cancel out because it's on the reactant side here and the product side here. The water would cancel out. We've got 6 H2O here and 6 H2O here. And nothing else cancels out. So we've got our phosphorus plus our oxygen plus our hydrogen. So those are the free elements that are going to be used to form the phosphoric acid on the product side. So we have to add these reactions together. Oh, I forgot to say, we needed to multiply this reaction by 3 so that the waters cancel out. Sorry, it was up there. I forgot to say it. So if we multiply the second reaction by 3, we also have to multiply the energy by 3. So we end up with our phosphorus, plus we've got 5 oxygens here and 3 oxygens here. That gives us 8 oxygens. Plus 6 hydrogens gives us 4 phosphoric acid. And the value we get, there should be a negative sign here. I'm not sure where the negative sign went. This should say negative 4497.2. But that's per 4 moles of phosphoric acid. When we talk about figuring out the standard enthalpy or standard free energy value for a substance, it's per 1 mole. So we would have to divide everything in the reaction by 4 to make this 1 mole, which means we'd have to divide the energy by 4. And again, there should be a negative sign here. There's a negative sign in the answer. So negative 1124.3 kilojoules per mole would be our answer for the formation of 1 mole of this compound from its elements. It's essentially like Hess's law, if that looks familiar from Chem 1.